Okay, next section here. There are some practice problems over those Born-Haber cycle problems. If you, um, hopefully, you've worked some of those. We'll probably, or we've worked them together. But this is the next and last section, which is about ozone, and this is really weird. So IB sets up these curriculums, and they used to have an environmental chemistry unit. And what they did is they broke little pieces of it up and they put it in all of the different units. And so, for whatever reason, they put ozone in this unit. And so, I don't know why, but we're going to talk a little bit about ozone. And it's a very, very, very weak connection to bonding, but there is a connection. So, first of all, what the heck is ozone? Well, ozone is O3, and you have O2 and you have O3. And so O3 is not what we breathe. It is actually poisonous, and it is going to be in the atmosphere. And what it does is it is going to protect us from various levels of radiation. So it says ozone, O3, is a gas in the stratosphere. So right here. So not where we're at, but above. So in the stratosphere. And it's essential for life because it traps heat, creating a temperature appropriate for life. So part of the atmosphere is the fact that it keeps the heat on the planet. So unlike other planets with lesser atmospheres, weaker atmospheres, or no atmosphere, it's substantially warmer here, so we can live, unlike on the moon. And so it does help keep the planet livable temperatures, but it also blocks, and this is the important bit, it blocks some of the dangerous radiation from the sun, right? So if we look at this graphic here, here's the sun, right? And not to scale, right? Because the Earth is not as big as the sun. But what happens is there's three types of ultraviolet light: UVA, which is bigger wavelengths, less dangerous; UVB, medium wavelengths, a little bit more dangerous; and then UVC, which is the smallest wavelengths and the most dangerous. And so this UVC never gets to the Earth because the ozone absorbs it, 100% absorbed. Most of the UVB is absorbed, and we just get the UVA. So what ozone does is it hangs out and it absorbs the dangerous radiation, or for IB, it's going to absorb the higher energy, smaller wavelength radiation. Okay. Now, so it says O3 will absorb radiation, and then we can just go down here. It's going to absorb radiation from the 100 nanometer, right there, to the 315 nanometer range, which is the dangerous stuff, right? We don't want that down here giving us skin damage. Now, an interesting about the O3s and the O2s is that you can break apart your O2s and you can create these O's with a dot. And so this is like this, like an O with a dot. So that's like a lone pair, except for there's only one electron. So normally it's like this, right? But a free radical is an oxygen with a single, it's got that one electron like that. And then we're going to call that, the way we're drawing it, we're going to call that a free radical. And a free radical is a highly, highly, highly reactive item. So it's looking to react. So if you look, when oxygen breaks down, it breaks down into two of these free radicals. Okay. And so you can break down the O2, and then what can happen also is that you can also have your O3s broken down as well, and they create these free radicals. Okay, now you can see, well, we're going to look right here. We can see the breakdown of O2 involves shorter wavelength than the breakdown of O3. The difference is due to the relative strengths of the O-O bond in the two molecules. So we're going to look on this next page because I couldn't fit it right here. Here's the deal. O3 basically looks like this. If you draw it out, it's going to look like this. And so if you count 2, 4, 6, 8, 10, 12, 14, 16, 18, that's 18, and 18 is your target number, 6 times 3. And this is a resonance structure, so this double bond could then go over here. It can bounce around, but that's what it looks like. Now, for this chapter, and I think this is the only reason they put it here, that is weaker than this. So it's got that single bond, which means it kind of has a weakness compared to this. So when you're looking at ozone right there, it has this weak point, and that weak point is where it can get broken. And so let's look at what happens. So it's broken apart by the longer wavelength, lower energy. The oxygen is broke apart by the shorter wavelength, greater energy. So from a standpoint of why they put it here, I think it's based upon the bonds. And the idea is that the ozone is better. It's better at absorbing the higher energy. It's broken down by the lower energy. And that's because it just has a weaker bond. And so the O3 is just a bit weaker because of that single bond. Not a lot, just a little bit. Okay, now it says catalytic destruction of ozone. It says ozone's ability to absorb UV radiation also makes it unstable, and it reacts easily with compounds released into the atmosphere. So because it's kind of unstable, it can react with other chemicals, and those other chemicals can pose some problems. And so the problem is it reacts with things that we release into the atmosphere, or it can react with chemicals released by human activities. So when O3 changes into O2, so like if it gets broken down, when O3 changes into O2, then you're losing some O3 and it's going to thin the ozone layer, which leads to more UV radiation reaching the Earth. So in the 70s, they kind of discovered, and I don't remember if it's the 70s, but definitely it was a big deal. In the 70s, they looked at the Earth and they did imaging, and they could see kind of the thinning of the ozone. It's not a hole. It's not like a hole in the ozone. It's not like, oh, we got this hole and stuff can get in. It's just a thinner part of the atmosphere where there's less ozone. And that can lead to more UV radiation getting in, which is dangerous because it can create cancers. It can create too much of an increase in temperature, etc. But we don't want that UV. We don't want those dangerous UVs down here, right? We don't want this UVB and UVC. And so if you thin the ozone layer, you're just allowing more of the dangerous UV in. So anyway, so in the 70s, the scientists were figuring this out. And there are a couple chemicals that we produce that are a problem. Here's the test question. The thing that we produce that's the biggest problem now are the nitrogen oxides. So N and any combination of O's. So nitrogen oxides are produced from vehicles. So a combustion engine produces these nitrogen oxides. And if you look at this reaction, if a nitrogen oxide comes into contact with ozone, it breaks down the ozone into O2. And it creates this NO2 free radical. The NO2 free radical can find some oxygen free radicals in the atmosphere. And look, it just makes another NO free radical. So here's the problem. This is the bad thing. This is the problem. It's the nitrogen oxides that we create with vehicles. If they go and they break down ozone and then they recreate themselves by finding other free radicals of oxygen, then we just get this system that will repeat itself. And so this is a loop that can be a bit of a problem. So car exhaust can be a problem in terms of allowing dangerous radiation into the earth. We're not talking about the greenhouse effect. We're not talking about global warming. We are not talking about CO2 here. Do not answer this question on tests with CO2 because that is wrong. We are talking about ozone, which is going to protect us from things like cancers and that extra radiation we don't want. We're not technically talking about global warming or CO2, which is what you hear about in the news. So there are other problems with combustion engines, many problems, obviously. And so this is an issue that can break down the ozone. Now, also, the other chemical that's also extremely problematic for the ozone are called chlorofluorocarbons. These were mostly used in refrigerants, so like your air conditioner in your car, air conditioner in your home. They used to use CFCs to make foam containers to put fast food in, so hamburgers and French fries and everything came in these foam containers. They used CFCs to create that foam, and so that created all of this waste in this foam and all these CFCs that were in the atmosphere. So basically, they figured out that, again, here's the CFCs. They're also do the same thing. See this? They create these chlorine-free radicals. They find the O3s, they break them down, and then look, they replenish themselves again with these oxygen-free radicals. So it's just this loop again. But the nice thing is that the scientists came together and the world basically banned CFCs. So one of the reasons, like you used to be able to fill up your own Freon in your vehicle and stuff like that, it's a lot harder to do because those chemicals that were commonly used have been banned. And so CFCs are not as big of a deal. Answering this question on a test, the thing that is a big deal is the NOx, or the nitrogen oxides, because these are still around because we're all still driving cars. Now, the ozone layer can replenish itself, and it actually has done a great job of replenishing itself because we got rid of those chlorofluorocarbons. And so now it's just dealing with these nitrogen oxides, which are a problem because we have a growing population in the world, more cars, more driving, but ozone can also replenish itself. So you can take an O2 and it can find an oxygen-free radical, and if you take that oxygen-free radical and the O2, if you combine these back together, then you get your O3 again. And so that's what happens, is that the atmosphere does a great job of replenishing the ozone if it's not competing with too many human-made things that are making it so that it can't replenish as fast as it gets destroyed. And so anyway, that's sort of the idea. I think it's kind of a weak tie-in, but this is really the reason. And so in the test, they're going to talk about which one breaks down easier, O3, so it's lower energy, bigger wavelength, or what is the problem now with breaking down ozone,